So this next section, section 2.3, which I've memorized its name, is called monotone convergence theorem. There's all about this theorem right here, but first let's talk about what it means to have a monotone sequence. And it's really a fairly simple idea. So a sequence AN is said to be monotonically increasing provided that every term is greater than or equal to its previous term. So if the sequence stays the same or gets bigger and bigger as it goes, then it's monotonically increasing. If it stays the same or gets smaller as it goes, it's monotonically decreasing. If it's either monotonically increasing or monotonically decreasing, then we just call the entire sequence monotone. Make sense? Let's just test real quick. What kind of sequence is this? Monotonically decreasing. And a sequence like this is monotonically increasing. What about a sequence like this?
It's not monotone.
Is that both?
It's monotonically increasing and monotonically decreasing. What is this sequence? Pi, 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 pi. Every term is either greater than or equal to the previous term. Similarly, every term is also less than or equal to the previous term.
So is
And
there
it's
any
called what?
sequence? What are some sequences that aren't monotone? Oh. Okay.
Right?
You're saying that's neither.
This is neither monotonically increasing nor monotonically decreasing.
So what's that one called? Pi.
This is both monotonically
So there's
increasing
not a word for it.
and monotonically decreasing.
Okay.
No, we don't have a term. I mean,
So what's the word for
if
that
it's
one?
both those, then it's just a constant. So that could be the special name for a sequence that's both monotonically increasing and decreasing. It's just a constant. This one's monotonically decreasing, this one's monotonically increasing. Monotone just means it's one of the two. So if I tell you a sequence is monotone, you're not sure if it's monotonically decreasing or if it's monotonically increasing, but you know it's one of the two.
So monotonically decreasing is every term is less than or equal to the last term.
The previous term.
And then increasing is just flip that.
Increasing is every term is greater than or equal to its previous term.
Okay.
Yep. So they're pretty straightforward ideas. Now, the whole heart of this section is this proof. So, if you have some sequence that converges and it's monotonically increasing, then the thing it converges to is a supremum if and only if the sequence is bounded. So if I have a monotonically increasing sequence that converges and it's bounded, then it converges to a supremum. Similarly, if I have a monotonically increasing sequence that converges to its supremum, then it's bounded. And then similarly with decreasing, but we're not going to bother with that case because it's the same. So I'm just going to do the proof for monotonically increasing. There's a second proof for monotonically decreasing, which is identical. So I don't think you need to see both. You understand?
I don't understand why we have to prove, well, the limit of an equals the supremum of an and an is bounded. Like, isn't that the same thing?
So this way, you're right, is really easy. So showing that if an is an is a monotonically increasing sequence. If the limit of an is equal to the supremum of an, then an is bounded. We already have that. 2, we already proved every sequence that converges is bounded. We just barely proved that, right? Which one is that?
The second proof.
This one. An converges implies an is bounded.
Oh, but we don't necessarily know it the other way around?
So now it's the other way that's a lot harder to get.
Okay.
So that's the heart of it. If I have a sequence that I'm guaranteed stays constant or increases, and it's bounded from above, then it converges to its supremum.
Isn't the limit of an and the supremum of
Aren't the limit of an and the supremum of an the same thing? No. I have 1 over n, its limit is 0, but the supremum of this,
No, it was 1.
yeah.
Right.
So no, it is not always the case that the limit of an is equal to a. We're going to show that the limit of an is its supremum, if and only if it's bounded from above and it's monotonically increasing.
Oh, okay, that makes more sense.
Good? So this way is trivial. Now let's do it the other way. Three, assume that an is bounded. What does that give me? That gives me that there exists some m such that the absolute value of an is less than that for all n, right? There exists some m in the real numbers such that the absolute value of an is less than or equal to m for all n in n. Every term in the sequence, when I take its absolute value, is less than or equal to whatever this m is. That's what it means for an to be bounded. Right? So I'm using the fact that an is monotonically increasing and bounded to show that it converges to its supremum. We follow that? Oh, there's a broken piece.
Hang on for a sec.
Yeah.
Don't be too much of that one.
I'll just write it. Oh, let me specify that. And we're done.
Oh, man.
Ooh. Okay, just make sure we're still lined up. Oh well. Okay, so let's go over this proof, and we'll recap from the top. So, let AN be some monotone. Over here, I said something I shouldn't have. I said, let AN converge. We don't need to use the fact that AN converges. So all I should have had is let AN be monotonically increasing. Then this is true. That's all we need. But that's what we have up here. So let AN be monotonically increasing. Then the limit of AN equals its supremum if and only if it's bounded from above. So I'll start out, let AN be some monotonically increasing sequence. Period. We already proved, we skipped a line. So to prove it this way, what do I need to do? I need to say, assume that the limit of AN equals a supremum of AN. Then we already proved that every sequence that converges is bounded. So I miss a line here. You understand how I miss a line? Okay, so that proves it this way. That's easy enough. Now this way is the heart of it all. So now I'm going to assume that AN is bounded. And I'm going to show that that leads to AN converging to its supremum. So assume that AN is bounded. What does it mean for it to be bounded? That means that there is some number m such that the absolute value of every term in my sequence is less than or equal to that number m. Right? And then we know if it's bounded, it's definitely bounded from above. We know that every sequence bounded from above has a least upper bound. Right? Completeness axiom. So since AN is bounded from above, it has a supremum, call it B. It has a least upper bound.
How do we know it's bounded from above? All it says is that it's bounded.
If it's bounded, then it's bounded from both below and above. That's what bounded is.
Right, okay.
Right? Because another way we can say this is AN is always less than or equal to M and greater than or equal to negative M. So bounded from below by negative M, bounded from above by M. But yeah, you're right, we could have just used the fact that it's bounded from above. We didn't need the fact that it's bounded from below. Anyways, since AN is bounded from above, it has a supremum, call it B. Now, let epsilon greater than 0. Here's my epsilon I'm grabbing. Because what am I trying to show? I'm trying to show that the limit of AN is this. So I'm showing it converges. So I need to grab some epsilon. And then I'm trying to ultimately show that AN minus B is less than epsilon for all n greater than or equal to some index, right? So get my epsilon. Here's ultimately what I'm trying to get, where B is the supremum of AN. Since B is the supremum of AN, then B minus epsilon is not the supremum. This is the least upper bound. Anything smaller is not an upper bound. So since B minus epsilon is smaller than B, it's not an upper bound. That means that there is some index in the sequence such that AN, there is some term in the sequence, call it A sub big N, such that B minus epsilon is less than it, right? B minus epsilon is not an upper bound. That means there is some term in the sequence greater than it. Now, since this is monotonically increasing, then if this is true at A sub big N, this is true at A sub big N onwards. It's true at A sub big N plus 1, A sub big N plus 2, A sub big N plus 3, because since it's monotonically increasing, we can only make this number bigger. We can't make it smaller. So then this is true. Are you good with this line? Okay. So if this is true from some n onwards, that gives us this. How do I know that AN is less than B? sorry, less than or equal to b.
Because B is the supremum.
Because b is the supremum. So we already know that a is less than or equal to b. That's always true for any n. We got this part's true from some index onwards. So this is definitely true from some index onwards. So when we add epsilon over here, that gets rid of the less than or equal to, right? So that makes it just strictly less than. So this is true from some index onwards. You follow all that?
Yeah.
And then, I'm sure you can see how to do it from here. Rewrite it so that it's negative epsilon is less than a and minus b is less than epsilon. Basically subtract b from all three sides. This is how we get this. This is true from some index onwards. That's the same as this being true from some index onwards. That's exactly what it means to converge. Follow all that? And then the corollary is just exactly what you expect. We're not going to prove that because it's almost identical. Let an be a monotonically decreasing sequence. Then the limit of an is equal to the infimum if and only if it's bounded. Make sense?
Mm-hmm.
Nothing weird? Any questions? Anything you want to go over again? Good to just push forward? Okay. Oh, that's the eraser I like.
I have a random question.
Let's just set this code over here.
How do you add two sequences
How do you add them?
together? And how do you times them together?
So when you have a sequence, then you know how to get the nth term. Right? So when I talk about the sequence 1 over n, this tells me how to get the nth term. It's identical to multiplying functions together. You do it all the time. And so if this is one sequence, 1 over n, what does this give us? This gives us 1 over 1, comma, 1 over 2, comma, 1 over 3. Now let's look at another sequence, just n. This gives us 1, 2, 3. Notice if I multiply this with this, I get n over n, or I just get 1. That's identical to multiplying the individual terms. 1, 1, 1. So you can just multiply the sequences themselves together the way you expect, and it's still going to generate it as if you multiplied the individual terms.
Really? So weird. Okay, how do you add them?
Same exact thing. The sequence I get if I added these individual terms is the exact sequence I'd write out if I wrote 1 over n plus n.
1 over n plus n?
Yeah, I could just write out the sequence 1 over n plus n. This is a perfectly valid sequence.
Oh,
What's the first term in the sequence? 2. What's the second term in the sequence? 3 halves? No. 2 5 halves? And I could keep going, right? And what I would write would be exactly what I'd write if I wrote this sequence first, and then this sequence, and then added each term. So, adding up works exactly how you expect it to. Very intuitive, and multiplying all the arithmetic we do.
okay.
Okay, and I'm erasing all this. Okay, so now we're just going to do some examples of using this one theorem over and over again to see applications of it. So don't be confused here. We're talking about a special sequence in at least these two proofs. We're doing a sequence where we sum up the terms of some other series, or of some other sequence, which is what we call series. So, do we understand what this sequence is saying, or should we write out some terms real quick? Let's just write some. What's the first, looking at this proof, maybe write what we're going to be proving over here, so we don't get confused. Proof, I'm proving as n by the nth term is equal to the sum from k equal 1 to n of 1 over k times 1 over 2 to the k converges. How am I going to show that this converges, by the way? I'm going to show that it's monotonically
Decreasing?
increasing. We're going to be adding up as we go. I add more and more terms. The
Oh.
terms I add get smaller and smaller, but it's increasing.
Right.
So if I can just show that's bounded from above, then it converges. We don't know what it converges to. Notice that this doesn't give me anything about what it converges to. It just tells me that it converges. Well, I know it converges to supremum, whatever that is.
Wait, you're gonna use that theorem to prove this?
Yeah, I'm going to use this theorem to prove all three of these.
Okay, can you explain how you're gonna use that theorem? That doesn't make sense to me.
So here I've got a sequence. I know it's monotonically increasing.
Right?
So if I can show it's bounded from above, then we're done.
Okay.
Then it converges by that theorem. Okay, so let's write out some terms in the sequence just to make sure we understand it. What's the first term in the sequence?
1/2.
1/2. What's the second term in the sequence? Well, it's the first term plus, what do we get when we plug in 2 here?
1/8.
1/8. And then the third term in the sequence is 1/2 plus 1/8 plus, what do we get when we plug in 3?
Wait, no, it's not 1/2.
And 1 over.
The first term?
The third one. Why is K 2? Okay, I'm done. I don't know.
Let's,
1 over K?
rather than writing it this way, let's write it this way. So, S sub 1 is equal to the sum from k equals 1 to 1 of 1 over k times 1 over 2 to the k. Right? So the first number we're plugging in is 1, and we're going to keep plugging in until we get to 1.
Oh.
So overall, we're just going to get one thing. So 1 over 1 is 1, times 1 over 2 to the power of 1, all said and done is just 1/2. So that's the first term. Let's look at the second term. S sub 2 is equal to the sum from k equals 1 to 2 of 1 over k times 1 over 2 to the k. What's this equal to? Well, when you plug in 1, we already know, okay, that's 1/2. And then when you plug in 2, that's going to be 1/2 times 1 over 2 to the 2. So 1/2 times 1/4 is an 8. So when we plug in 1, we get this. When we plug in 2, we get this. We stop when we plug in 2. That's what S sub 2 is, whatever that sum is.
Wait. That did not make sense.
You start
Oh.
k at 1. When you plug in 1, you get 1/2. Plus, because it's sigma, you keep going until you get to 2. Plug in 2. 1/2 times 1 over 2 to the 2. That's a k.
Oh, so you're saying for the first one you did, the second one? Okay, so for 1 over K is 1 over 1 times.
1 over 2 to the 1.
So that was confusing. I did that. But okay, I get that. So
Which
there's,
gives us 1/2.
there's 2 different terms because it's times unit or what?
Well, it's sigma. Sigma, you start here, you go up.
Oh wait, no. Okay, right.
Okay.
That's so dumb. Okay.
Yeah, it's dense notation.
Okay.
So let's do one more term to make sure we got it. S sub 3. What's this equal to? It's the sum from k equals 1 to 3 of 1 over k times 1 over 2 to the k. Well, when we plug 1 in, we already know we get 1/2. When we plug 2 in, we already know we get 1/8. When we plug 3 in, we've got 1/3 times 1/8 is 1/24. So that's S sub 1. So our sequence, the sequence Sn, whatever it is, we know our first term is 1/2. Our second term is What's a half plus an 8? 5/8. We know our third term is whatever this all adds up to. So 12, 15, 16, 24ths. And it keeps on going.
What does this sequence converge to?
Oh no, I want to say 1/2. No. I don't know.
No, it gets closer and closer to 1, doesn't it?
Maybe. I'm not sure. All right. Anyways, so there's our sequence. So we're proving that this thing converges. What it converges to, we don't care right now. Okay. So, I'm not sure how we want to say the first part. First, we need to state this thing's monotonically increasing. So, what's the best way to say that? S of n plus 1 is equal to S of n plus 1 over n plus 1 times 1 over 2 to the n plus 1, which gives S of n plus 1 is greater than S of n, which gives monotonically increasing. Something like that. Right? S of n plus 1 is going to be S of n plus the next term. This is always a positive number, therefore this number is bigger than this number.
Was that line basically proving that's monotonically increasing?
Yep, if S of n plus 1 is greater than or equal to S of n, it's monotonically increasing.
Oh, okay.
The typical way that you prove that sequence is monotonically increasing, probably should have just done it that way, is you do a sub n plus 1 minus a sub n and show that's greater than or equal to 0. So that's probably what I should have done. So I should have written this minus this is equal to this, which is greater than or equal to 0, therefore it's monotonically increasing. I think that's more clear. Sorry.
Except the definition says exactly what you did, so that's more clear.
Well, both of them imply this.
Right.
It's just going from this to implies this to S of n plus 1 minus S of n is equal to 1 over n plus 1 times 1 over 2 to the n plus 1 is greater than or equal to 0 is what we mean by this is greater than or equal to this. That was our definition for greater than or equal. So,
Okay.
but it works. As long as you understand everything I'm saying. Okay. So, we know that it's monotonically increasing. Now we just need to show that it's bounded from above. Right? It's going to be bounded from above by 1, I think. Is that what I use here? Yeah, it is. So then I say, observe that.
So you couldn't ever get 1 in that sequence?
Yeah, you can't ever get one in sequence. So observe that. Basically, first thing I'm going to say, I'm trying to simplify this expression, only making it bigger. So I'm going to say S of n is less than or equal to some other sequence, is less than or equal to some other sequence. Keep doing that until we find a sequence that we know for sure is less than or equal to a number. It's kind of like when we're showing something converges. You start out with some complex thing and you keep saying, but we know whatever it is, it's less than or equal to this, is less than or equal to this, is less than epsilon. Similar thing here, we're going to show this is less than or equal to this, is less than or equal to this, is less than some number, and so we're good. So observe that S of n is less than, we don't even need less than or equal to, would be less than just the sum from k equals 1 to n of 1 over 2 to the k. In other words, or less than or equal, this 1 over k term only makes it smaller. Right? So that is less than or equal to that. I'm going to have to evaluate that.
Yeah, that's right.
So we already know how to evaluate a geometric sequence. Flashback for a second. R to the 0 plus R to the 1 plus R to the 2 plus dot 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 plus R to the n minus 1 is equal to
I can't remember.
R to the n minus 1 all over R minus 1.
Yeah.
If we take this and multiply it by this, everything's going to cancel out except for R times this and negative 1 times this, which is going to leave us with that. So maybe I'll write this so that you can see it this way. What is this right here? This is 1 over 2 to the 1 plus 1 over 2 to the 2 plus 1 over 2 to the 3 plus 1 over 2 to the 4, right? Plus 1 over 2 to the n is where it ends. Okay, so that is equal to, yeah, I don't have enough space over there. That is equal to R one minus, let me write it and then think for a second to make sure I got it right. 1/2 minus R minus 1 over R to the n plus 1, one more than where we ended, all over 1 minus R.
1 over R.
I need to use R there instead of 1/2.
Well, R in this case is, oh, thank you. 1/2. Sorry. I don't like how we switched that. Let's think for a second. So R to the 0 plus R to the 1 plus dot 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 plus R to the n minus 1 is equal to
R to the n minus 1, right?
R to the n minus 1 all over R minus 1. Is that right? Because we can always rewrite this term as just 1.
How do you know what R is?
R is just what we keep increasing the power by. Notice that 1 over 2 to the 3 is the same thing as 1/2 cubed. So if I plug in 1/2 for R, I get this sequence.
Okay. So
Almost, I'm missing
R is
1 because we start at 1/2, right?
Okay, but you can't switch R.
So this
and-
is equal to this minus 1.
Is it supposed to be 1 minus R on the top? R to the n, 1 minus R to the n. Something is different.
Right.
This is the geometric series formula, right?
So this is, yeah.
Well, this says that it's different than what you have right there. It says, that's the-
Oh, because 1 minus. Okay, you can do it either way. Okay. I'm with you. So it says 1 minus r to the n, right?
Yeah, or 1 minus.
Over 1 minus r. And you can do it either way. If you factor out -1, -1, that flips it, which is how I had it before. Now, all we're missing is, I have a 1/2 here, we have a 1 here, right? And that's because we're missing a 1. So this is equal to this minus 1, because we don't have a 1 in this term. So 1 minus a half is a half. Let's just see what we get when we do it. 1 minus that plus 1.
Is it plus 1?
Yeah, because I don't have the 1 over here.
So shouldn't it be minus 1?
Minus 1 from both sides, yes. So if 1 plus all this is equal to this, then all this is equal to that minus 1. Can I do that?
Why is it 1/2 to the power of n plus 1 instead of to the power of n, like you have in your formula below?
All that matters is if this goes to n, then this goes to next power. This just has to be 1 more than this. I could have set to n minus 1 and then called this 1 to n. This is just going to be 1 power higher than wherever this ends.
Why is
Oh,
that again?
because your other formula, the sequence ended at n minus 1.
So our formula is r to the 0 plus r to the 1 plus r to the 2 plus ... plus r to the n minus 1 is equal to r to the n minus 1, or 1 minus r to the n, these are logically equivalent, all over 1 minus r. Right?
Right.
But this one doesn't start with a 1, it starts with a 1/2. I guess I could factor 1/2 out of all this. And then it starts at 1, right? So it's equal to 1/2 times that.
There we go.
That should work. Anyways, let's keep going with it and make sure we get something good. Except for that's not technically true. I have a 1/2 right here, which I know that's the typical way to do it. You just do the first term in the sequence minus that to the n plus 1 over 1 minus r. But I'm trying to see how we get that from this. Oh, my 1/2 thinking works. Okay. If we were to factor 1/2 out of all this, then that also makes this an n instead. So that would be 1 minus this to the n, because if we factor an 1/2 out of all this, then this ends at n minus 1. There we go. So then it's 1/2 times this, distribute the 1/2 in, that turns this into a 1/2, and that turns this into an n plus 1. Okay, so everything I've written on my paper, there is no mistake. Ah. There we go. Okay, so then that is equal to that. Now let's do some simplifying. We'll split this into two things. Well, 1 minus a half is just a half, right? So we have 1/2 minus 1/2 to the n plus 1 all over 1/2. That's equal to 1 minus 1/2 to the n. Right? Now, when we subtract this, we're only making it smaller. So this is less than or equal to 1.
3.
There we go. Okay. 3. Therefore, S of n is, therefore the absolute value of S of n is less than or equal to 1 for all n in n. Therefore it's bounded, therefore converges. Therefore, Sn is bounded, which gives us Sn converges. And we're done. Sorry. Way too much work going from that to that. Should have seen that quicker. How's that, lab? Everything good? Alright, let's do the next one. This one is actually a pretty interesting and famous one. So, for example, let's just think intuitively for a second. When I give you the sequence 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... You know that gets closer and closer to what?
Gets closer to 0.
1.
Oh, plus. My bad.
Yeah, we're adding these up.
Yeah.
This gets closer and closer to 1. Now, I know if I do something like 1 plus 2 plus 3 plus 4, obviously this is tending towards infinity. So the question is, a natural question is, what kind of sequences can I start creating that still converge? How big can I make them and still have them converge and not take off towards infinity? Right, so what do you think? So this one we were doing the series 1 over 2 to the n. What about this one? What do you think of this one? 1 plus 1/2 plus 1/3 plus 1/4 plus ... Where do you think it goes? Do you think that gets closer and closer to a number, or do you think it takes off towards infinity?
It's closer.
Do you think that this tends towards some number a, or do you think it takes off to infinity?
I think it tends towards A.
We got 1 says it converges to a number.
I think it goes to infinity.
You think it goes to infinity? We got a tiebreaker?
The answer's on the board.
Yeah, the answer's on the board. Does not converge. You can cheat. Alright, so it does not converge. It tends towards infinity, and that's what we're going to show now. This is called the harmonic sequence, and in some sense it's like the smallest thing that still, when it doesn't converge we say it diverges. When it tends towards infinity we say it diverges. This is, in some sense, the smallest series that still diverges.
Why?
Huh?
Why?
Why?
Why is the smallest one? Is there not? There's no smaller one.
Well, it's not really the smallest because you're like, okay, get rid of one term. Well, that didn't change anything. It still tends towards infinity because infinity minus the constant is still infinity. But it's in some sense the smallest. It's somehow the middle of, if you're to line up all the ones that converge and all the ones that diverge, then this is somehow in the middle of them. I don't know if that is just confusing you. Never mind. Let's show that this thing, this harmonic sequence, diverges. How am I going to show that it does not converge?
Why? Do you know
1 over 1 plus 1/2 plus 1/3.
Yeah.
I know that these are called harmonic because they give this pattern. The sequence goes back to basically the earliest versions of music theory, the harmonics that you get by looking at certain intervals
Yeah, that makes
of a
sense.
string.
Right, because each time it, yeah, okay. So that probably came back from like a long time ago then.
Oh yeah, very old stuff, going back to Pythagoras,
Yeah, that makes more sense.
possibly sooner. Okay, so proof Sn, the sequence or the series Sn by the nth term is equal to the sum from k equals 1 to n of 1 over k does not converge. How can I show that it doesn't converge looking at our theorem?
You're using the contrapositive of that?
This converges if this converges to this if and only if this is bounded. So that means this is not bounded means this does not converge.
Right.
So we need to show that this is not bounded. And I know I had two proofs written down how I wanted to do this. Let's see. First observe, oh yeah, that's. So let Sn by Sn equal to blah blah blah, k equal to 1, n 1 over k, 2, then s of n plus 1 minus s of n is equal to 1 over n plus 1 is greater than or equal to 0. That gives us s of n plus 1 is greater than or equal to s of n. That gives us s of n is monotonically increasing. Good with all that logic so far? The series is monotonically increasing. Now we just need to show it's not bounded.
Okay.
All right. So, let's see. I just tried to show you a pattern, I guess, before I give you it in general. Observe that s of n is equal to 1 plus 1/2 plus 1/3 plus, let's see, how far do I go? All the way to the 9th to help see the pattern. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus dot dot dot. Okay, so it's equal to that, which is less than or equal to, well, strictly less than, 1/2 plus 1/2 plus, oh no, 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/16 plus dot dot dot, which is equal to,
So random.
it will here in a second. That's why I wanted to write a bunch of terms to help see the pattern. Okay. So notice I can replace a third with a fourth.
Why?
and that only makes it smaller.
Oh, okay.
So, oops. Oh yeah, because I'm showing it's going to be greater than this. S of n is equal to this, is definitely bigger than this, because we just made that smaller. We turned 1/5 into an eighth, 1/6 to an eighth, 1/7 to an eighth, 1/8 stays an eighth. Then a 9th, a 10th, 11th, a 12th, a 13th, a 14th, a 15th, and a 16th are all going to just be 16ths now. So basically we're going to end up with 1 1/2 term, 2 1/4 terms, 4 1/8 terms, 8 1/16 terms, 16 1/32 terms. And so when you add up the 2 1/4, the 4 1/8, the 8 16ths, the 16 32nds, etc., you're just going to get 1/2 1/2 1/2. So this sequence, whatever it is always greater than this, which we know is going to tend towards infinity. Right? If I add 1/2 an infinite number of times, that keeps making it bigger and bigger. I can eventually get bigger than any number you want. So now, here's the in general. That would just help you see the pattern. In general, S sub, where do I have you written? Up here. S sub 2 to the k, 2 to the k, is going to be greater than or equal to 1 plus that many k 1/2. So in other words, pick a k, 3. I'm saying S sub 8. What's S sub 8? That's 1 plus 1/2 plus 1/3 plus 1, all the way to 1/8. S sub 8 is greater than or equal to 1 plus 3/2.
Okay. It doesn't seem very, like, it makes sense, but it doesn't seem like we've really proved that besides giving that example. Does that prove it okay? Does that work?
Yeah, you could have gone straight to this. This is always true. And most people would have understood, yes, it's just you're not used to working with series, so I want to write out the pattern first.
Like, it makes sense, but how do we prove that? How does that logically follow?
I mean, you could do an inductive proof if you wanted to explicitly show it.
So we just need to take that and say, okay, this is true, let's move on.
If you want to show that this is always greater than or equal to this for every natural number n that you plug in there, yeah, you could do a proof by induction to do that. It'd be pretty straightforward.
Okay.
So, in general, this is greater than or equal to this thing. And then I assume let n be any number you want. We can always get a term in the sequence greater than that number. Or you can just say, since this is unbounded, then this is unbounded. I don't know. Is that too much?
Yeah, that's why in the sequence we're trying to prove is unbounded.
We're showing that S is unbounded. And I know that once you get to this term, it's always greater than or equal to this. So here's how I can say it. Let n be any real number you want. Then there exists n in n such that 2n, do I want 2n? No, I want n greater than 2n. Right, that's just the Archimedean property. For any number you pick, I can always find a natural number n bigger than it. Well, what does that give me? That gives me that s sub 2 to the k is greater than or equal to, 2 to the n is greater than or equal to 1 plus n times 1/2 is greater than n. So for any number you pick, I can find a term in the sequence such that it's bigger than that number. Therefore, it's not bounded.
Why is that middle part bigger than n?
Why is this bigger than m?
Yeah.
N is bigger than 2m.
Oh.
So half of n is bigger than m, and then when you add 1, it's still bigger.
Okay.
Sorry, I probably should have done the algebra better. Good?
I have a question. Where did you get s to the 2 to the k?
That is just what I'm observing from this pattern. I'm saying s sub 2 to the k is always greater than or equal to this.
Okay,
So in other words,
what is that right there? 1 plus k times 1 half? What's that?
just a number. So pick a number k. 3.
Okay.
So what's 2 to the 3?
8.
So I'm saying the 8th term in s sub n is greater than or equal to 1 plus 3 halves. So what is the 8th term? That's 1 plus 1 half plus 1 third plus 1 fourth plus 1 sixth plus 1 seventh plus 1 eighth. Here's the 8th term in this series. And I'm saying that this is greater than or equal to 1 plus 3 halves. This is greater than or equal to 1 plus 3 halves.
Okay. That makes sense.
Okay. And then, so for any m you pick, I can always find a term in the sequence greater than that m. Therefore, it's not bounded. Therefore, this doesn't converge. Rather than showing my proof by contradiction that doesn't converge, even though it's nice and simple, let's move on to the last proof and then maybe come back to it. That way we finish the section. Was this the last section of chapter 2?
I think
I
so.
think so.
Oh, 2.4.
Okay. Just 2.4?
Yeah.
On week 8, you have review chapter 2 and then chapter 2 test. Does that mean that we're spending like an hour on review and then?
I don't know. We'll figure out what we're going to do next week. Okay. 2.3. Yes, we're still on 2.3. Now I'm doing this. Okay. Our last proof. Proof if the absolute value of c is less than 1, then the limit of c to the n is equal to 0. 1. If c is equal to 0, comma, then the limit of c to the n is equal to the limit of 0 to the n is equal to the limit of 0 is equal to 0. So handle the special case if c is 0, then obviously this is true. Good? Okay, so now to assume, let's do another case, assume c is greater than 0.
The absolute value of c?
No, just c is greater than 0. And observe that, so I know that, so assume c is greater than, so we handled the case where c is equal to 0, now let's look at the case where c is greater than 0. Well, since the absolute value of c is less than 1, I know that c is between 0 and 1, right?
Is c just some number?
Yeah. Oh, sorry.
Yeah, it's not the
I forgot my beginning line.
limit.
Let c in R such that the absolute value of c is less than 1. That should have been my first line, sorry. So let c be some real number such that this is true. And then we're going to handle first the case where c is 0, then this theorem is obviously true. Now we're going to handle the case where c is positive. If c is positive, then we still know that it's less than 1. So assume it's positive. What does that mean? That means that 0 is less than c, but it's still less than 1, right?
Okay.
Which is going to give us that c to the n is monotonically decreasing. Right? Because c is some fraction. C is some number smaller than n. So every time you multiply by something smaller than n, you make your term smaller. No? Okay. If c is less than 0, then look, c to the n plus 1 minus c to the n is equal to, factor out the c to the n, we get c to the n times 1, or c minus 1, is less than 0. Or less than or equal to 0, therefore it's monotonically decreasing. The next term minus the previous term gives us a number less than or equal to 0, it's monotonically decreasing. C to the n plus 1 minus c to the n. Factor out the c to the n, we get c minus 1. C is a number smaller than 1. Minus 1, that's negative. Positive number to the n is still positive, times negative is negative, less than or equal to 0.
Okay.
So it's monotonically increasing.
Right, okay.
In general, pick any number between 0 and 1. 0.9. I'm saying the higher exponent I put here, the smaller I make the number. 0.9 to the 2 is a bigger number than 0.9 to the that. Because every time you multiply by something smaller than, not smaller than 1, you make the number smaller, smaller, smaller. Let's write it out to make sure that you can see it. What's 0.9 squared? That's 0.81, or 81 over 100. You can think about this as 9 over 10. Now what's this? That's 9 to the whatever this is, over 10 to whatever this is. I need 5 zeros, right?
So which one's bigger?
This is way bigger than that.
No, this one's bigger than this?
This number is way smaller than this number.
Okay, right, that's what I thought.
Let's just do a smaller one
You said it
to
different a
see how
second
quick it
ago.
happens. Let's look at, just happens when you cube it. 0.9 cubed, that gives us, let's see, 81 times 9, what is that? 729, did I do that right?
Yeah.
729 over 1,000. So now we have 0.729 when before we had 0.81. And as you keep going, making that higher and higher, you get a smaller and smaller number. But if that wasn't already obvious to you, then you can just always do it this way. The previous term, or the current term minus the previous term. If that difference gives you something positive, then this is greater than or equal to this. If it gives you something negative, then this is less than or equal to this. And if it gives you 0, then they're equal. You with me? Okay, so we're good with the idea that this is now monotonically decreasing. And then, 3, observe, I'll just say it, observe that c to the n is bounded from below by 0, right? A positive number to a power is always still just a positive number. I can't take a positive number, put it to some exponent, and suddenly get a negative number out of that. Every time I multiply by a positive times a positive is a positive. Positivity axiom, right? Are you just zoning out?
No, that makes sense.
Okay. So, therefore, the limit of Cn is equal to its infimum. C to the n. Oh, it was a corollary to this.
Right.
If n is monotonically increasing, then its limit, if it's monotonically increasing and bounded from above, then its limit is its supremum. If it's monotonically decreasing and it's bounded from below, then its limit is its infimum.
Okay.
So I know that the limit of this is its infimum. Let's see. I need to show that the infimum is now 0. So I need to show that 0 is the greatest lower bound of this, and we're done. I know it converges to whatever its infimum is. If I can just show that 0 is the infimum of it, then we're done.
Okay.
I need to show 0 is the greatest lower bound. Okay. So, 5. We'll do that by contradiction. Assume, by way of contradiction, that the infimum of c to the n is greater than 0. So I already know that the infimum is greater than or equal to 0. How do I know that? Because I know 0 is a lower bound. 0 is a lower bound. The infimum is the greatest lower bound. So I already know that the infimum is greater than or equal to 0. I'm going to assume by way of contradiction that the infimum is greater than 0. Show that leads to contradiction, therefore it's equal to 0.
When did we find out that 0 was lower bound?
We just stated it. A positive times a positive is always a positive. So
Oh.
observe that is bound from below by 0.
Okay.
Good? Okay. So, assume by way of contradiction that the infimum of that, let's name it so that I have something to reference. We'll call it B equal to B is greater than 0, so I don't have to keep writing infimum over and over again. Okay, 6. Now let's get our contradiction. Then c to the n greater than or equal to b gives us c to the n plus 1 greater than or equal to b. How can I say that? Oh, just the next term in the sequence. Every term in the sequence is greater than or equal to b, in other words. So I'm just looking at 2 terms in the sequence. So I don't know why I didn't imply arrows. I should have just said and. So grabbing 2 terms in the sequence that are consecutive terms, they're both greater than or equal to b. Now that gives us that c to the n plus 1 over c is greater than or equal to b. Oh, greater than or equal to b over c. Yeah, that's the same thing as that. I don't know why I'm referencing that. Which gives us that c to the n is greater than or equal to b. What was I thinking here? Is greater than or equal to b over c. For all n.
Why not? Maybe.
So I'm saying, if b is the greatest upper bound, look, I found a bigger upper bound. Because when you divide by a number smaller than 1, you make it bigger, right? So I know that, and I know that. just canceled out. Oh, there's nothing weird here. Is there anything weird here?
No?
That just messed with my brain for a second, but I realized I didn't do anything weird. It's just from writing back and forth.
Makes sense. Why are we using that?
Okay, so we got c to the n is greater than or equal to b over c. B over c then is a lower bound, and it's a bigger lower bound than b. So that gives us c to the n is greater than or equal to b over c is greater than b. Right, if b were 0, then this isn't true. But since b is a positive number, then this is true.
So you're saying that b can't be a positive number, it has to be 0.
Right, so we assumed it was positive, which makes this an inequality rather than an equality.
And that's false.
So now I found something bigger than b that is the lower bound of this.
Okay.
And b is supposed to be the supremum. So if I allow b to be greater than 0, then b over c is bigger than b, which would then become a lower bound, which doesn't work. So there's our contradiction. So 7, therefore the limit of c to the n is equal to 0. In this case, next case we do 8, we do assume c is less than 0 now.
Well, did we already show that?
Then the limit of negative c to the n, with parentheses, because now that's a number greater than 0, is equal to 0. And the absolute value, comparison lemma real quick, absolute value of c to the n minus 0 is equal to the absolute value of negative c to the n minus 0 is less than or equal to that's all we need for the comparison limit. And then, so this converges to this.
Wait.
So assume that c is some number less than 0. So then we just barely showed that this converges to 0.
How? Because of what we just did above?
Yeah. If c is less than 0, negative c is greater than 0.
Which is basically what we just did.
So a positive number to the n we already know converges to 0. And then, so we already know that this converges to this, and this is equal to the same thing, but we could write less than or equal to if we want.
Why are they equal?
Multiplying by negative 1 isn't going to change the absolute value.
Oh. But it'll change it inside. Isn't it going to change it with the exponent?
The absolute value of x is equal to the absolute value of negative x.
Right. That's not what I'm confused with. I'm saying c to the n is not necessarily going to be the negative of negative c to the n.
Yeah, well, it'll be the positive or the negative. C to the n, negative c to the n can be rewritten as negative 1 to the n times c, which is either times by negative 1 or it's not. So this is equal to this, take the absolute value to the n, sorry.
There we go.
And then the absolute value of the product is the product of the absolute values. So that's the same thing as the absolute value of -1 to the n times the absolute value of c. We don't need parentheses over here now. Do a dot so we can see where the absolute value is. Times the absolute value of c to the n. Right, and then this is just 1. And then rewrite the -0. So, same thing, right? Okay. So, that's the end of that. That's all the theorems that we were covering in this section. So, you can use the rest of class to go over homework. Or ask me any questions.
I have a question on homework.
For the homework that we're currently covering?
Yeah.
Okay, let me turn this off.